Physics is often seen as a daunting subject which tends to scare many. Astrophysics and astronomy even more so. Is seen as a very complex and incomprehensible field. Many people enjoy learning about space, but are rubbed the wrong way by the technicalities of the discipline. This is the series for those people, as well as anyone aspiring to study these topics later in life. Over the course of 12 episodes, one per month, we will be covering the basics of astrophysics and astronomy, providing a good introduction for the beginner. There are not many prerequisites for this course except for a basic understanding of math. If there is any slightly complex math anywhere, I will link resources explaining it below. Additionally, each video will be supported with notes for the reading and sometimes worksheets for those who are seriously pursuing the field. I want to start the first episode with a few simple ideas, laying out the basics of the fields. Firstly, we must define how astrophysics is different from astronomy. Astronomy is seen as the simple study of any objects in the universe beyond Earth. Astrophysics is more specific, studying the physical processes of these objects. In modern physics, an understanding of astrophysics is key, whether one wishes to be an astronomer, astrophysicist, or a physicist in general. Astronomy as a field has existed for millennia meanwhile, even going as far back as the Greeks, while astrophysics as it is known today started with scientists such as Isaac Newton and Johannes Kepler. A quirk of astrophysics I want to cover before we talk about measurements is the coordinate systems. Astrophysics uses three kinds of coordinate systems: Cartesian, altitude azimuthal, and galactic. Cartesian coordinates are the ones you're exposed to in school with perpendicular x and y axes, and the z axis in the case of astrophysics. The altitude azimuthal system is a system with the Earth at the center, two angles, an altitude being the angle from down to up, and an azimuth, an angle from left to right, are taken to map objects in the sky. A similar system is used for the galactic coordinate system, with the key difference being that the Sun is at the center instead of the Earth. Today the latter is used, as geocentric coordinate systems are not very reliable in results compared to heliocentric ones, as the position of the Earth relative to the stars moves a lot more than the Sun relative to stars outside of the solar system. One last thing before we talk about measurements is modern technology we use to measure. You may know of telescopes such as Hubble's and James Webb. However, there are other telescopes also crucial to astronomical measurements. Two of particular importance were the Hipparcos before 2015 and the modern Gaia Space Telescope, and many others across the entire Earth and also in the Earth's stratosphere. The first kind of measurement crucial to astrophysics is distance. When you talk about objects in space, we want to know how far away they are, as this is often the first step to understanding other parameters. A crucial way we measure close-by distances is called parallax. To understand parallax, I need you to take your thumb, put it in front of your eyes, use the other hand to close your left eye. Now, without moving that thumb, cover the right eye instead. What you will notice is that the position of the thumb changed ever so slightly. However, it was not because you moved your thumb, just changed your perspective. The Earth's orbit can be thought of as being our metaphorical eyes in this situation. Every 6 months, we know the Earth completes half an orbit, meaning it is on the opposite side as it was 6 months ago. As such, the angles that the object occupies in the sky also change. These angles are the altitude azimuth and the galactic coordinate angles that we discussed earlier. By taking this change in angles, which is a very small change, we can find the parallax angle. This works up until the object if it is a star for around 13,000 light years away. When we know this angle, as well as the fact that there is a certain radius of Earth's orbit around the Sun, we can define the distance to the object using geometry. These angles, by the way, are extremely tiny, and thus they are measured in seconds and arcseconds. If you're wondering what that is, 1 degree contains 60 minutes, 1 minute contains 60 seconds, and 1 second contains 100 arcseconds. As such, 1 degree has 3600 seconds and 360,000 arcseconds. By taking the tangent at small angles, tan x approximates to x. This is a nice quirk of mathematics, and thus we can define the angle as being the radius of the ratio of the Earth's orbit around the Sun to the true distance to the stellar object. Oftentimes these objects are stars, which are the beating heart of most astrophysical observation, as we will cover in episodes 2 and 3. However, this is where we once again face a massive roadblock, as we did not know the distance to the Sun. Despite that, astronomers defined a particular quantity of distance that is still used today. I don't want to spoil what that is, even though the title is in the second episode. Rather, I would like you, yes you, to think. If you were an astronomer facing this roadblock, how would you define a unit of distance without knowing the distance to the sun? Is there something you could do? This is the question that ends this video and is answered at the start of the next one. The second episode will focus on this mystery unit, as well as the measurements of stellar parameters or the properties of stars. The special focus on stars is going to be prevalent for a few episodes due to most measurements either being off or dependent upon stars in some way. Till then, stay curious and look in the sky where objects drift over the seasons. Thanks for watching.